Hello everyone, welcome to the OneClass channel. My name is Marlyn. I'm a second year student at the University of Waterloo studying chemical physics. Today we'll be going through some commonly asked chemistry questions at both the high school and college level. Be sure to check out the links in the description if you're in need of any extra homework help or would like some one-on-one tutoring. So for our first question, we will be figuring out the best Lewis structure for CH2O. Okay, so first off, we'll have to figure out the index of hydrogen deficiency. And this is going to be equal to 2 times the number of carbons you have, plus 2 minus the number of hydrogens you have, minus the number of nitrogen, minus x. X represents any halogens you may have, all over 2. So if we're to put that all in, we have 2 by 1, because we only have 1 carbon, plus 2, minus 2, minus 0, minus 0. These two cancel over 2, and so we get 1. This indicates that we're going to have unsaturated, so we can expect a double bond somewhere. Okay, so next up we're going to want to count our valence electrons. And so from carbon we have 6 and we only have, 4, and we only have 1 carbon. From hydrogen we have 1, but we have 2 hydrogens. And from oxygen we have 6, but we only have 1 oxygen. So that's 12. Okay, so now we just come up with a sketch down here. Put that O here. We know already, we can make the quick note that oxygen is optimized to have 2 bonds. Okay, so we can start by putting in all single bonds. And any remaining electrons to fill all of the octets. And let's see if we get our 12. So we have 2, 4, 6, 8, 10, 12, 14. So obviously this is too much. And so let's cancel out both of these by adding in a double bond here instead, in order to get the valence electrons back down to 12. So let's just rewrite all of that. Okay, and then we count them down again. So 2, 4, 6, 8, 10, 12. Perfect. Carbon has a filled octet, oxygen has a filled octet, hydrogen and the other hydrogen are both satisfied, meaning that this is going to be the best Lewis structure for this molecule. Okay, so next up we want to find out what is a HOMO, which is the highest occupied molecular orbital. Let's just write that out. Okay, so of course when we're talking about the highest occupied molecular orbital, we will be dealing with the molecular orbital theory. So you're going to need to draw the MO diagram for the peroxide ion. And so first we should just count out the electrons that we should have for O2 2-. And so typically we would have 8 electrons for each oxygen, so times 2. And then because of the -2, we're going to add 2 more electrons. And so this is going to give us 18 electrons. And so we can just do 9 electrons per O2 1-. Okay, and so if we begin to draw our diagram here, we'll have energy. Going to have O2- and O2-. And that's going to be our 1s, our 2s, and lastly our 2p. And we're just going to fill them exactly as we should, so we know we have 9 electrons for each. So 2, 4, 6, 8, 9. So 2, 4, 6, 8, 9. Perfect. This one will be filled the exact same way. Okay, and then next up we want to form the molecular orbitals right here. So we're going to have a sigma 1s, antibonding sigma 1s, sigma 2s. Let's just move these a bit lower. Sigma 1s, antibonding sigma 1s, sigma 2s, antibonding sigma 2s. And then we are going to have our pi 2p. Seems a little bit crowded here. Let's just space everything out a little bit more. Okay, and then let's go ahead and label them. So sigma 1s, antibonding sigma 1s, sigma 2s, antibonding sigma 2s, pi 2p, sigma 2p, antibonding pi 2p, antibonding sigma 2p. And then let's just go ahead and fill in all of those electrons. So we have 4 here to distribute among 4 places, so they'll all be filled in. Another 4 in 4 spots. And now we have 2, 4, 6, 8, 10, and we have 2, 4, 6, 8, 10, 12 spots. So we're going to fill these 2. So that's 4, 5, 6, 7, 8, 9, 10. So obviously the highest occupied molecular orbital is going to be this one. Because it's of the highest energy compared to all of the rest. So our answer is going to be antibonding pi 2p. And that's going to be B. Okay, for our next question, we want to figure out the Lewis structure for IBr2 minus. And so we need to remember to count that negative charge when we're counting the valence electron. So let's start with that. So for our valence electrons, we will have 7 coming from the one iodine plus 2 by 7 because it's a 2 bromine, and then we're going to add 1. So let's just label them. And this is because of the charge. And this is going to give us a total of 3 by 7, 21 plus 1, 22. So I have 22 electrons to distribute. So obviously we're going to put I in the middle, Br. Let's not start with the bonds, but I in the middle, we're going to have Br and Br. We do know that halogens like to make a single bond. Let's start with a single bond on each and try and fill out the rest of the valence electrons. Okay, and then let's see if it all makes sense. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. And so we see that we need 2 more electrons. And we cannot fit them on the bromine, but we will be able to fit them on the iodine in such a manner. And what you have here is actually called an expanded octet. Which only certain elements are permitted to have. So if we just quickly look at the periodic table, so elements beyond period 4, so including period 4 and beyond period 4, are going to be allowed to have something called an expanded octet, where it can accommodate for more than the 8 electrons. And the reasoning for this is because, so the reason why we say it can take 8 electrons at a time is because we usually have the s orbital taking 2, and we have the p orbital taking 6. But once we start having d orbitals, which occurs from period 4, including period 4, downwards, then you can make space for 10 more electrons. And so they say at the first year undergrad level that the d orbital is the reason why you have an expanded octet. It's more complex than that. But for now, just keep note that elements including period 4 and downwards can have an expanded octet. Above them cannot. So if this was something else like lithium for whatever reason, I wouldn't be able to account for those 22 electrons, but I wouldn't have 22 valence electrons to begin with. So this is going to be our final answer. Oh, and don't forget about we have a minus. Let's figure out which one that is on. So 2, 4, 6, 7. So 7 minus 7, 0. 2, 4, 6, 7. 7 minus 7, 0. 2, 4, 6, 7, 8. So here it will be 7 minus 8, which would give us minus 1. So the one negative charge is going to be on the I. And that's it. Okay, next up, we would like to get the formula for aluminum nitrite. So what we're going to do is use the crisscross rule, and that's when we're using when we have an ionic compound. We're going to use its oxidation / reduction state in order to get their formal charges. And so if we have element X, for example, and element Y with these respective charges, then we're just going to crisscross them. And when they combine, you get X, B, Y, and these are subscripts. Subscripts like you see in H2O. So for H2O, we have H that has a positive, plus O, which has 2 minus. So when you crisscross them, it becomes H2O. The two charges cancel because positive and negative, and that's it. And so for aluminum, we know that it is in group 3. So group 3 metal, which means that its charge will look like that. And for nitrite, we have a list here of common ions like hydroxide and sulfate and nitrate, including and phosphate, and they just have commonly known charges. So for NO3, it's going to be NO3 minus is what it's known as its charge. So when you just combine those two, we're just going to crisscross it like that. So Al will have a 1 here, and the 3 is going to apply to the entire thing. So not just the oxygen, so that it can become NO6. It's going to apply to the entire thing. So it's going to become NO3, 3. And so let's just write that up here. Sorry, it's NO2. Because we're doing nitrites, not nitrate. 62. And then if you just rewrite that in a cleaner form, because you don't need to write down the 1. And that is what the formula would look like. And just to give what this means, is that in order for things to be balanced chemically, same way that it was H2O, whenever we have H2O, it's oxygen and 2 nitrogen. The same thing is going to be applying here. We'll have aluminum connected to 3 nitrites, not with covalent bonds, but with ionic bonds, whenever you do have the molecules. And so that's what it would look like. Okay, on to the next question. We are looking for the Lewis structure of CH3+. So we can first calculate the valence electrons. And so we're going to have 1 by 4 because of the carbon, plus 3 by 1 because of the hydrogens, and then we're going to subtract 1 because of this plus charge. That's going to give us 4 plus 3 minus 1. And that is going to give us 6. And I need to find a way to distribute those 6 electrons. So let's give us C, H, H, H. And let's start with some single bonds. And fill in the octets, for example. So this would be 2, 4, 6, 8. That's too many. So what we're actually going to have here is an underfilled octet. And that is what is going to be responsible for that positive charge, because carbon has 4 valence electrons. We have 1 from here, 1 from here, 1 from here, and it's missing that 1 more. So it's going to be 4 minus 3, leaving us with that plus 1. So this is what our final answer is going to look like for that one. On to our next question. We want the Lewis structure for CH2Br2. So again, we start with the valence electrons. So from carbon, we're going to have 4. And this is just by 1 because we have 1 carbon. From hydrogen, we're going to have 1, but that's going to be multiplied by 2 because there are 2 of them. And from bromine, we're going to have 7, but then there are 2 of them again. And so that's going to give us 4 plus 2 plus 14, and that's just a flat 20. Now let's figure out how to distribute them. You may be wondering why I chose this configuration specifically and not, like, for example, BR here. And that actually relates back to Vesper theory, which I'll get into in a second. And so let's just connect them with single bonds. And so we see the carbon is happy, hydrogens are happy. Let's fill in our octets and see if all of those valence electrons have been accounted for. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So yes, they have been. And we don't have any formal charges because 2, 4, 6, 7. So the 2 bromines are going to be happy. Hydrogen has 1, when carbon has 4, 4. So there's not going to be any net charge. Now the reason why I put the bromines across from one another is to... So Vesper theory is just a quick way to figure out what the geometry of the molecule would actually look like, and it's configured to minimize repulsion between electrons, because we always favor the lowest energy configuration of a molecule. And so if we don't minimize that repulsion, then we're not minimizing the energy of the molecule. And so in this case, I want the bromines across from each other because these lone pairs, if they're next to each other, would repel each other a lot. So we want to keep them as far away from one another to minimize that repulsion. And so this would be the best answer if you just leave it like that. Okay, for our next question. So we want the Lewis structure for this. So again, we need to count valence electrons. And so this is in group 15. So you're going to have 5 multiplied by 1 from that, plus 3 multiplied by 7 from the fluorine, because each have 7 valence electron and there are 3 of them. It's going to be 21 plus 5, which is 26. So we have 26 electrons to figure out where to place them. So of course, let's put the AS in the middle, surrounded by the 3 Fs, and let's start with some single bonds. And then let's fill in the octets for each of the fluorines because they're optimized for 1 bond and they have that already. Okay, and then let's see if we have any electrons left over. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 22, 24, 5. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So we have 2 more left over, and that makes sense. AS does not have a filled octet, so the last 2 electrons just go right there. And we won't have any formal charges because 2, 4, 6, 7. So just in case you haven't been understanding how I've been counting those formal charges on each. There's going to be the number of valence electrons minus the number of lone pairs minus the number of bonding pairs, but over 2. Because remember, F is only contributing 1 electron here, and AS is contributing the other one. Maybe unequally or equally, that isn't our business right now. And so for F, we're going to have 7 minus 2, 4, 6. So 6 on the lone pairs, 7 minus 6, minus has 1 bonding pair, so the bonding pair has 2 electrons in it over 2. And so 7 minus 6 minus 1, and that's 0. On AS, you're going to see something similar. All of the F's are the same, of course. 5 valence electrons minus the 2 lone pairs minus 2, 4, 6 over 2. And so that is 5 minus 2 minus 3, and that was also 0. So we have no formal charges, and that is our final answer. Okay, next up, we want to find all of the possible Lewis structures for butane. So here we just need to note the fact that it's butene. That can easily be done by noting the structure of the formula, CnH2n with n is equal to 4, which is the but. Okay, and it's an E because of this fact. So we have butene here. And so butene, of course, has isomers depending on if he decides to make other singular chains, like you'll see. So first, let's draw the main structure. And we will have 1 double bond. So let's put it on the further side for now. And so this will be able to make 2 more bonds with hydrogen. 1, 2, 3, 1 more bond with hydrogen. This can make 2 more bonds, and this can make 3 more bonds. So what this is called is, if we count this way, and we're going to have to count this way because we want to encounter the double bond as soon as possible, this is going to be but1 ene if we label it. Next up, let's decide to move this double bond. And so let's have the double bond here instead. So this will be able to make 3 more connections. This will be able to make 1 more, 1 more, and 3 more. You can double check on each that you have 8. So 4, 4, same thing here, 4 by 4. And so now, if we, no matter which side you decide to come at it from, you're going to encounter the double bond on the second carbon. So here was on the first, that's why it was but1. Now it's on the second. So its label is going to be but2 ene. Okay, and now we can actually start creating links. Okay, so let's say we decided to, we can't move this carbon here because if you did, it would just be the exact same thing because I could just fold it back, if that makes sense. And so let's actually move this carbon link here. And so if we do that, we have that carbon linked here, a double bond C. And so this can make 2 more connections. This can make no more connections, because it already has 4. This can make 3 more. And this can also make 3 more. Okay, and so this is going to be labeled differently. We're going to want to count from this side to encounter the double bond as soon as possible. If that double bond wasn't here, you'd be able to count from any side to encounter the methyl group on either side. And so this would be, has a methyl, 1, buttes on carbon 1. Oh, no, it's no longer buttes. Now the main chain is 3, so it's going to be prop. And that's what you have. So these are the 3 options. There's nowhere else where you could take this third one, because if we put it on the other side, what we have is this one just flipped over. And so we can only have these 3. Okay, next up, we want to find the electron configurations for each of the following. I'm just going to write them out over here. Okay, and then you can use the periodic table or Madelung's rule. Periodic table is the easiest one to use. If you want the shorthand, I'm going to start with the shorthand. And so the closest noble gas to chlorine is neon. So we're just going to put neon in middle square brackets. And then we start counting. So this is going to be 3s2, 3p1, 2, 3, 4, 5. So 3p5. So 3s2, 3p5. If we'd like the entire thing written out, you can start from the top, which would be 1s2, 2s2, 2p6, and then that 3s2, 3p5. And so 1s2, 2s2, 2p6, 3s2, 3p5. Land on chlorine. Okay, our next one. Sp, let's find it first. And it's right here. Okay, so the nearest noble gas, of course, is going to be krypton, right here. So you can't go to the one after it, you have to go to the one before it, and that's going to be krypton. We just put the krypton in square brackets, and then you begin counting again. So, SB is here. It's in the 5th period. So we're going to have 5s2, 4d10, and then 5p3. So 5s2, 4d10, 5p3. If you want to write out the full thing from the top, then again, you just count. So 1s2, 2s2, 2p6, 3s2, 3p6. Sorry, skip the 4s. Here it seems. 4s2, 4p6, 5s. Sorry. I did include the 4s. Sorry, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, drop the number down by 1, so 3d10, 4p6, and then 5s2, 4d10, drop the number by 1, remember, and then 5p3 to get to SB. And then we have W, so let's find it. It's going to be right here. So we're going to have to pass some lanthanides, which include an F group, which is not too hard to deal with. And so if we want the shorthand notation, we need to find the closest noble gas. That's going to be xenon. So we have xenon. And then we have 6s2. And then we have the lanthanides, so drop it by 2. So 4F lanthanides can take 14. 5d10. Oh, we're not going all the way. So now that we're in the 5D group, we realize that it stops on the third one. So it's actually going to be 5d3. And that is going to be the final answer. Five D3, sorry. This is included. So 1, 2, 3, 4, 5D4. And then that's it. Yeah. And then if you want to write out the entire thing, as I said, just count from the beginning. So you're going to hit all the way until you get 5P6, and then you start the 6S2, 4F14, 5D4. Next up, PV. We want to find it first. Find that's going to be right here. Closest noble is Zanon. Let's just put that in the square brackets. And then now we need to get to it. So again, we're going to be passing 6S2. 4F14 with the lanthanides. 5D10 because we get out of the transitions. And then we're going to have 2 here. That's going to be 6P2. And that's it for that one. And then lastly, we have CF. So again, we're going to need to find it. And it's actually inside of the lanthanides here. And so for the lanthanides are going to come before the D group when you're listing them down. So because we technically have not hit the D group yet, we're just going to have the S group. It is in this second row. So it's going to be in period 7. So you will have 7S, and then drop the number down by 2, so 5F, then just count them. 2, 4, 6, 8, 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 5F10. And so again, find the closest noble gas, that's going to be Rn. And then we're going to have 7S2, drop the number down by 2, 5D10. And that's going to be our final answer. And that's it for this question. 5F, sorry. The labels can get a bit confusing if you are rushing. So just be careful. But that, it's F. 10. Okay, next up we would like the Lewis structure C2H3N. And so we can check out the index of hydrogen deficiency. We know that that's 2 by C plus 2 minus H minus N minus X, with this being halogens all over 2. That's going to be 2 by 2 plus 2 minus 3 minus 1 minus 0 over 2. So 4 plus 2 minus 3. Sorry. And this is not going to be equal to 0. So we do know that, sorry, let's just ensure that I've done this correctly. 2 by so since it's not going to be equal to 0, we will have a double or a triple bond somewhere. So now let's, as we typically do, begin by counting valence electrons. And so from carbon we have 2 by 4, plus 3 by 1 because of the hydrogen, plus 5 because of the nitrogen. So 8 plus 3 plus 5, and that's going to give us 16 electrons that we need to figure out where to place. So let's just start with this general skeletal structure. And we can put single bonds between them with the hydrogens around 1. And so we just start with that, okay? And so if, for whatever reason, we decided to fill in the octets like that, we'd see that it's over 16. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So let's start by getting rid of 4 of them. 2, 4, 6, 8. Yeah. And then let's see, 2, 4, 6, 8, 10, 12, 14, 16, 18. So we're still going to be 2 over. So we can deal with this by getting rid of those 2 and having a double bond like that. Another bond like that. So 2, 4, 6, 8, 10, 12, 14, 16. Perfect. All of them are accounted for. We can check out the formal charges on all of them. Hydrogen has 1 valence electron, 1 electron in a bonding pair, so that's 0. Same thing for the other 2. Nitrogen has 5, 2 coming from here, 2, 4, 6 divided by 5 minus 2 minus 6 over 2. And that's going to give us 5 minus 5, and that's 0. Lastly, on the carbon, we have 1, 2, 3, 4, and again 1, 2, 3, 4. So no formal charges left over. That's going to be like this with a net charge of 0. Okay, next up, we would like the half reaction. So the cell diagram for the reaction occurring in silver zinc button batteries is like that. We'd like the half reaction that involves silver, the half reaction that involves zinc, write the balance for the net cell reaction, and the cell potential, the standard potential of the cell. Okay, so if you know how to read cell diagrams, it should be read as such. So let's just write it out first. Okay, so if we could label it, the left-hand side of it represents oxidation. The right-hand side of it represents reduction. And what is in the middle is whether we're using an acid or base solution. So you can note it down when you're writing the half reactions, what you're providing the hydrogen ions with. And so in this case, of course, you'll be using a basic solution because KOH is a basic solution. So for the half reaction that involves silver, that's going to be reduction. And so we have Ag2O solid going to Ag solid. We can start out by balancing our oxygens. And so if you'd like to balance our oxygens, we know that we're balancing them with hydroxide ions, so plus OH minus. Next up, we'd like to balance our hydrogens. And so we see that we have one H here, but no H on the other side. And so we'd add H2O. And then we're going to multiply this by 2 because here we have 2 in the H2O. And so 2OH minus minuses and aqueous solution. Okay, so oxygen is fine, hydrogen is fine, but what's left is a charge. And so here we have a charge of 2 minus, and here we have a charge of 0. So we're going to balance that out using electrons. So that it can become Ag2O solid plus H2O liquid plus 2 electrons to give us Ag solid plus 2 OH minus in aqueous solution. And that's going to be the half reaction that involves silver. Next up, we'd like the half reaction that involves zinc. That's going to be oxidation. So I'm getting these effects purely off of reading the cell diagram. And if you'd like confirmation that you're doing things correctly, just remember oil rig. So oxidation is the loss of electrons. So oxidation is loss, reduction is gain. So here we have reduction, and we see it's gaining electrons to become something else. In our oxidation half, we're going to want to see the loss of electrons. So we're going to want to see electrons on the other half of the equation. And so from our cell diagram, we know solid zinc is becoming solid zinc oxide. First up, we're going to want to balance oxygen. We're balancing oxygen with hydroxide ions because of the basic solution. So OH minus in aqueous solution becomes solid zinc oxide. Next up, we want to balance the hydrogens. Since we're going to add H2O to the other side to do that, we have 2 hydrogens, so we're going to want to multiply this by 2. So everything, all of the mass species are balanced, and next up we're going to balance charge. And so here we have 2 minus, we want 2 minus on the other side, and that can be done by adding 2 electrons. And so as expected, we're seeing electrons on the second half of the equation. And so for the net balanced equation, we don't need to multiply any of them by any common factors because the electrons lost equals the electrons gained, so that is okay. And so you just want to add these two. So let's just write it out here. And here. Okay, and so this is our reduction half and our oxidation half. And so when we add them, we would like to cancel out any common factors. And so we have 2OH appearing on both sides, H2O appearing on both sides, 2 electrons appearing on both sides. So for our final, we get Ag2O solid plus solid zinc to form solid silver plus solid zinc oxide. And this is going to be our final equation, our final net balanced reaction. And next, we want to calculate the standard potential of the cell. So this actually has an equation too. And so the standard potential of the cell is equal to the standard potential of the reduction half minus the standard potential of the oxidation half. We know what half is what, so the reduction half is the silver half. So that is going to be Ag2O becoming Ag minus that zinc becoming zinc oxide. And so these values will be provided in the textbook usually, but usually they're provided in the form of reduction potentials. And so if you have the reduction potential, the oxidation potential is just the negative of that. And so you'll get a value of 3.342 for the silver potential. And with the zinc potential, you're going to get a value of 1.26 volts, but then remember that's the reduction potential, so the oxidation potential is going to be the negative. And so those two add up to get you 1.602 volts as the standard potential of the cell. And that's it. Okay, and this is going to be our last question. We'd like to figure out the pH of a 0.42 molar NH4Cl solution. The Kb for ammonia is 1.8 by 10 to the negative 5. So first, we're going to need to account for the dissociation of ammonia. Sorry, of the solution that we're given. And all of this is, of course, in aqueous solution. Okay, and so, of course, here we're going to have a 1 to 1 to 1 ratio that we just need to know. Next up, we need to account for the formation of ammonium ions. And this is just through Bronsted-Lowry the reaction that represents it. So you just add NH4 plus H2O liquid. So just a typical acid-base reaction. Plus NH3. Okay. And so since we need the pH, and the pH is equal to the negative log of H3O plus, and we're dealing with H3O plus generally in this equation, instead of the Kb, we need the Ka. But that's totally okay because we can calculate it quickly from the value that we're given. we know Ka times Kb is equal to Kw. And so Ka will simply be equal to Kw over Kb. Kw is 1.0 times 10 to the negative 14 over the Kb that we're given, which is going to be 1.8 times 10 to the negative 5. So our Ka is going to be 5.56 times 10 to the negative 10. Okay. Now, next up, we're going to need an ice table for this reaction to figure out what the concentration of those hydronium ions is. And so, H3O plus and H3. Now, we already know what concentration we start with of NH4 plus, and the reason for that is because of the 1-to-1 ratio here. So 0.42 to 0.42. So then we have 0 of this and 0 of this. Okay, and this means that we're going to be subtracting x here. And this will gain some amount, and this will gain some amount. We don't know what that amount is. So at equilibrium, we will have these concentrations. And so since, because of the fact that Ka can also be written as this, so it's the rate constant for this acid-base reaction. And we know what K is. It's 5.56 times 10 to the negative 10. We simply plug in these values at equilibrium into this and solve for x. Okay, so H3O is going to be x by x over 0.42 minus x, and that's going to be x squared over 0.42 minus x is equal to 5.56 times 10 to the negative 10. So from this relation, we can tell that x is going to be pretty small, and we can verify that at the end, which means that subtracting it from 0.42 isn't going to make that much of a difference in our calculation. And so we can actually forget about this and just write it as x squared over 0.42 is equal to 5.56 times 10 to the negative 10. Now from there, simply isolate for x. And we get x is the square root of 5.56 by 10 to the negative 10 multiplied by 0.42, meaning x is going to be 1.53 times 10 to the negative 5. And so this is going to be our concentration of hydronium ions at equilibrium. And so next up, we simply plug that into our pH equation. We're going to get the negative log of 1.53 times 10 to the negative 5. And this is going to give us a value of 4.82 for the pH. And that's going to be our final answer. Okay, and those are all of the questions that I have for you today. I hope you enjoyed today's Q&A. If you'd like to be a part of any more videos, be sure to hit the subscribe button and the bell next to it so that it lets you know when we do post. If you'd like to post questions of your own, check out the links in the description for the OneClass links. This has been Marlyn from OneClass, and I hope